Hello everyone, welcome to the video. Today we are going to solve the problem minimum insertions to form a palindrome. In this problem, we are given a string and we have to return the minimum number of characters that we should insert such that this string becomes a palindrome. This problem again tests the very fundamental approach of problem solving: recursion, dynamic programming, memoization, and then bottom up approach. If we get comfortable thinking through this, we can use this approach to solve a large number of tough problems which are based on the same technique. We are going to solve this problem today. We won't directly jump to the solution, but we'll go through the thinking process and build the solution. We discuss the questions of data structures and algorithms on this channel in simplest words with fundamental approach. If you are new to this channel, please subscribe. Let's start. To begin with, let us first note the key things given in the question. We are given a string S and we have to find the minimum characters that we should insert in this string such that this string becomes a palindrome. So if we consider an example, if we have the string AB, we just need one more character. Why? Because ABA will become a palindrome. Similarly, if we consider another example, ABCD, then for this we need 3 characters to be inserted to make this a palindrome. So if we consider our solution as a black box, we are getting a string S as an input and we have to return an integer as an output. So what will our function signature look like? Our function signature will look something like this. Let's start thinking about this problem. We can see that the brute force or the simplest approach that we usually take will not be easily applicable here. Why? Because there are multiple characters. Every character can be inserted into multiple positions. So with brute force there will be too many combinations and it will become complex to iterate over each of them. So what do we do? Let us try to break down our problem into smaller problems. What do we mean by smaller problem? Since our input is a string, a smaller problem would mean a smaller string. So our aim will be that if somehow I can get answers to my smaller problem, can I use them to solve my original problem? Okay, let's try breaking it. Let's say someone comes and gives me the answer to this subproblem, this smaller subproblem of BCD. They come and they tell me that, hey, you just need to do M insertions to make this a palindrome. Can I use this knowledge to compute the answer for my original string? This is already a palindrome with M insertions, so I just need to insert another A. So answer will be M plus 1 insertions. Now what have I done here? I have successfully used answer of a subproblem to compute the answer of my original problem. How did I get the answer of my subproblem? That is not my concern right now. And this was an input of just 4 length string. This could be easily be a 40 length string and still the concept would remain the same. But this was just one way of breaking the problem down. We could have also broken it in this manner, ABC and D. And if the answer for ABC was N, our overall answer will become N plus 1. So now what should we choose among these two? Since our aim is to choose the minimum, we will choose whichever is minimum of the two. Now is that it? We have still left one case where the last letter and the first letter of the string are same. ABCD was a string with its first and last characters as different. So if our input was ABCDA, in that case, there would be one more way of breaking this string down into smaller problems. We will just eliminate the first and the last letters and we'll see how does the middle string do. For the middle string, if somebody tells us that you need to do O insertions to make this a palindrome, our overall answer will become O. So out of the 3, which one should we choose? Whichever is minimum. But this solution is eligible only if first and last characters are same. There is no other way of breaking this problem down into just a smaller problem except these three. Now all of these, whether it is ABCD, BCD, ABC or BCD here, all of these will go through the same method call that will give us answers like M, N, O or the minimum of these. So our next problem is how do we represent that input to that recursive method call? So if we represent ABCD as f of s I comma j, then what will be M? M will be f of s I plus 1 comma j. What will be N? N will be f of s I comma j minus 1. And O will be f of s I plus 1 comma j minus 1. So let us call these x, y and z for simplicity. X is f of si plus 1 comma j plus 1. So if I have to calculate f of si comma j, what will be its value? If the last and first characters are equal, then it will be minimum of these three. And if they are not equal, then it will be minimum of these two. So this is what we have so far. We know that if we have to find the minimum insertions to form a palindrome for a string between I and j, we can break it down into smaller problems, I plus 1 to j, I to j minus 1 and I plus 1 to j minus 1. If someone gives us solution to these smaller problems, we can calculate these. So what we have done here is we have identified the recursive relation. Now identifying the recursive relation is just the first step for a recursion problem. Let's check if we have identified the inputs as well. Have we? Yes, we know that whatever will be the recursive call, the inputs to that will be the same string, starting pointer and the end pointer that will denote the substring. Now with these two things in mind, let's try to see what is our algorithm so far. So this is our main function. This will only take string s. This will not take I and j. So we will have to define a new function that takes I and j as input as well. So let's say we define minimum insertions util. Now what will we pass? Since this is a string s as input, now we have to pass the whole string. So our starting pointer will be 0 and end pointer will be the last index of the string. So we pass this string and we have whatever will be the answer to this, we will return this. Now what will be algorithm like for this function? We will use this relation here. So since we have Sij, it is easy to check Si and Sj. Once we can check Si and Sj, we can also calculate x, y and z. To calculate x, y and z, we can see that we have to use the same method call. So we will use the same method call here. And we can calculate x, y and z similarly. So we have x, y, z, we have Si and Sj. Then can we calculate the answer to that? Yes, we can, and we can return the answer. But will this work? No, right? Because every call to this method is again calling the same method. So this will go in infinite loop. And how do we have to end this infinite loop? We need to define the terminating condition for this recursion, the base condition. And what is the base condition of a recursion? When do we get that? We get that when our input to this function is smallest. What will be the smallest possible input to this function? It will be a substring of length 1 or a substring of length 2. So what do we mean by substring of length 1 in terms of this input? When I and j are equal. And substring of length 2 means when j is just greater than I. Now consider substring of length 1. What will be the minimum insertions required to form a palindrome for substring of length 1? Substring of length 1 is already a palindrome. So minimum insertions required will be 0. While substring of length 2, let's say if it is AB, then we need just one character to form a palindrome, ABA. And if it is already AA, then we don't need any character to form a palindrome. Therefore, if the substring is of length 2, then we will need either 0 or 1 depending on the substring given. So therefore we can write the base condition. Now, with base condition added, our algorithm looks something like this. We first check if the substring is of length 1. If it is of length 1, then we return 0 because we don't need to insert anything to make these a palindrome. While if the substring is of length 2, then we check if the two characters are equal. If they are equal, they are already a palindrome and we don't need to make any insertions. So we return 0. If they are not equal, then we'll have to insert one character to make this a palindrome and we'll return 1. Now this recursive function is complete and will not run in an infinite loop because as input gets smaller and smaller, ultimately it will hit either of these two things. One interesting thing to note here is that for the base condition, we didn't just stop at the smallest length, that is length equal to 1. And we went ahead and also included length equal to 2 in our base condition. Why did we do that? We did that because it is possible that our input gets reduced by size 2. For example, here this is from I to j, and if we calculate z, it is from I plus 1 to j minus 1. So input is getting reduced by size 2. So we will need to take care of both till length equal to 1 and till length equal to 2. Because from length equal to 4, we could go to length to 2 and then length to 0. So we need an output. We need to return from length equal to 2. We are now done till step 3. Now we need to check if there are any duplicate or overlapping subproblems as we go through this recursion. What do we mean? We mean that when we are calling this recursive method again and again through different inputs, is it happening that we have called this method for the same input multiple times? So, for example, is it happening that we are calling this method for same I and j, let's say I equal to 500 and let's say j equal to 1000, we are calling this for this same substring again and again. Because if this is happening, that means we will have to go through this whole calculation multiple times for the same input, which will be inefficient. Now let's see if we have the overlapping subproblems in the way we have broken down our problem. We have broken down our problem into these 3 parts. Now if we go on solving this thread, we will have to solve for BC somewhere. If we go on solving this thread, we may again have to solve for BC. And similarly, here too we may have to solve for BC. Therefore, for BC we may actually have to solve thrice for the same input. Here, input was very small, just a string of length 4, ABCD. But input could be very large as well. If let's say the input was of a string of length thousands, then we will have so many overlapping subproblems, and for each of them we will have to solve these multiple times, which will greatly increase the time complexity of our solution. So we definitely should solve this. And how should we solve this? We can do one thing. Whenever we solve for an input, we store its answer somewhere. Let's say we solved for a problem P, we stored its answer somewhere. Now next time, whenever we encounter the same input, we don't go on solving this whole thing, but we return our answer directly from here. Now what data structure will serve this purpose best? Map. Why? Because whenever we give an input, we can return the answer for that input in just constant time from map. So with map in picture, now what will our algorithm look like? Before returning the answer, we will first put that in the map that hey, for this input, this is our answer, just like this. And here, before actually going to the calculation, we will first check that if map already contains this input. If map already contains this input, that means we have already calculated for it and we will return the answer directly from map in constant time. Now, to obviously do all of this, this function needs a map. So there will be one more input to this function other than these three, and this will be map. So we will call using map here and here as well. And to call using map here, we will have to declare the map with an empty map here in the first function. When we declare the map, we will also have to declare the data types of key and value. What will be the data types of key and value? Value is simpler. The data type of value will hold the answer to this recursive call. The answer to this recursive call is basically minimum number of insertions. So value is basically integer. The key must represent the input. Now S does not change with every recursive call. It remains same. What changes is I and J. So we have to represent I and J together in one single data type. Can we do that with existing data types? No, we cannot. So we will need to use a new kind of data type, such as a pair. So we will have to define a new custom class called pair, which will have these two members, int I and int j. Once we have that, we can declare the map of pair, integer. Now how will we use it? Before putting here in the map, we will declare a new pair from this input, new pair object, and then we will put that in the map. That means this pair class needs to have a constructor. And here, when we are checking that if the map contains the same input, we will again create a new pair p, and then we will check if map dot contains p. And if it does, we will return the answer. But let us think that whether this map dot contains p, whether it will work as expected, whether this will be able to find that old pair p that I would have saved in this map before returning. No, it won't be able to find it. Why? Because in Java, these variables of the class, these do not actually hold the values. These are only references to the memory addresses. So p in itself does not tell us anything about I and j. We can get I and j using p.i and p.j, but p itself refers to the memory address. So if here map dot contains p, it will try to search for this new memory address that we had just declared. So it won't be able to find the old memory address that we would have here when we had put that in the map. So what should we do? Our aim here is that we should be able to tell Java that when you are doing map.contains p, don't just go on looking for the same address that it points to, but instead look for the values that it represents, I and j. And how will we do that? For that, we will have to override the equals method of this class. By overriding the equals method of this class, we will tell Java that hey, the two objects of this class are equal when these values of the two objects are equal, and not just when their memory addresses match. And whenever we override equals method, we also have to override one more method, which is hash code. So there seems quite a bit of work that we have to do in the pair class. So let's see how will our pair class look. In our pair class, we will have the two members I and j. We will have a constructor which can be called from outside to construct a pair object. We will have getters to get the values of I and j. Then we will override the equals method. In the equals method, first of all, we check if the memory references of the two objects match. Which two objects? This O that is passed as an argument and the object on which this equals method was called. So if this is equal to O, we return true. Then we check if at least class of the two objects are same. Note that the input here is of type object. So we check if the class of the two objects are same. If these are not same, they cannot be equal. If we have determined that the class is same, then we verify that the two values I and j are equal for the two objects. If these are not, then only we return false. And whenever we override equals method, we also have to override the hash code method. So we are simply using this method here to compute the hash code 31 into I plus j. It will have some collisions, but it is definitely workable. So this is what our overall dynamic programming solution looks like for our problem, the minimum insertions to form a palindrome. While this may seem overwhelming together, but if we see it step by step, it seems a bit simpler. First of all, here we just put the recursive relation code. Then we put the base condition code here in the black lines. Then we thought of eliminating the duplicate calculations by using a map. So we put the map part here. Now while we were using the map to represent the key, we needed a new class pair. And to be able to effectively use the map.contains for a pair, we needed to override equals and hash code method. Now let's see what will be the time complexity of this method. It is difficult to calculate time complexity of this using our normal way because this is a recursive call. But we can think of it in this manner. For every substring possible, we have made calculations only once, because whenever we encountered that again, we returned it directly from the map in constant time. And how many substrings will be there? They will be of the order of n square, and hence time complexity will be order of n square. Similarly, space complexity will also be order of n square. Let us now summarize what all we did. First of all, we understood the problem with the help of an example. Then we tried to break down the problem. And we tried to analyze that if somebody could give us the answer to the smaller problems, can we solve the larger problem, or can we find the answer to the larger problem? And smaller and larger here was in terms of the input. So we could see that yes, this was possible. So we knew that we have to use recursion. And as first step of the recursion, we figured out the recursive relation. As the second step, we tried to identify the inputs of that recursive relation. And we figured out that in addition to the original string s, we will also need I and j as inputs to denote the starting point and the end point of a substring. Once we identified the inputs, we tried to write the algorithm. Then we realized that as the third step, we should now think about the terminating condition or base condition of the recursion. We realized that the base condition comes when our input is smallest. And here our input was getting smaller by length of the string. So we wrote the terminating condition for length 1 and length 2. Once we did that, our solution was complete. But it had very high time complexity because there were many overlapping subproblems and solving them again and again was very inefficient. To eliminate that, we came to dynamic programming and we used a map. So what we did was, before returning the answer, we put that answer into a map against an input. And whenever we were getting that input, before going through the full calculation, we first checked if that input exists in the map. If it exists, then we return the answer directly from the map. Now, to declare this map, we needed a new class pair to represent the key of that map, which is I, j. And to effectively use that map, basically using the map.contains function, we needed to override equals and hash code method of pair class. We also saw how to do that and how to write a custom pair class. We wrote the overall algorithm and estimated the overall time complexity. Now this is it for this video. In this video, we had discussed the top-down dynamic programming approach to this problem. In the part 2, we will discuss the bottom-up approach to the same problem. So please subscribe and keep watching. Thank you.